early mid-December before the students left, and they were absolutely determined that Hello, Houston. I have a guest for you today, a kind of a surprise. It's a little bit late because of my own ineptitude in organizing our time, but we have with us today Professor Ben Jansen from the College of Engineering, specifically as an electric engineer, and he's agreed to come in and talk to us about some of the issues that range broadly across cognitive psychology and his particular interest in it. So I would welcome you.
Thank you.
Thank you. And we'll eventually put you on the screen and then even show people what you look like. But you and I were kind of wandering around through the annals of what on earth the overlap is between cognitive psychology and your kind of more engineering interest in it. And I was fascinated by the discussion that we kind of got interrupted with here just now. And that is, it might be worth talking about how you ended up in an engineering perspective's interest in brain activity and things related to that, how you got to where you are, basically.
Well, by airplane.
See, other academics also engage in smart-ass remarks, too.
And I was explaining before we started, I did my engineering training back in the Netherlands. So I was born and raised over there. And when I was looking for a master thesis topic, I spoke to my advisor, and he essentially said, hey, there happens to be a project in Amsterdam that involves EEG analysis. You are an electrical engineer. You can do signals. Why don't you go there? I ended up going there. I ended up doing my PhD, and then I ended up somehow in the United States, and I've never left. And I'm still doing EEGs. Many years have passed since. If you ask me, have I invented anything? My honest answer is absolutely not. Have we learned anything? Oh yeah, a whole lot.
What kind of strategies in general do you tend to utilize where is the overlap in the fields?
The overlap in the fields between the engineering and
strategies for problem solving, for instance, and things like that.
I don't know how I'm solving problems. We define problems. The problem I've been working on for the last 10, 15 years is the problem of how do we respond to simple sounds that you may ordinarily not even pick up. Since if I tell you now, do you notice the hum of the ventilator? You probably didn't even notice that ventilator was going. Right? Your brain, your central nervous system has somehow inhibited the detection of that. If I make a sudden sound, you all look up. So if something unexpectedly happens, your brain reacts immediately. Now, how come? How can we suppress irrelevant information? How can we suddenly detect novel information? So as an engineer, we try to build systems that can kind of replicate that behavior. So that if the same monotonous input goes in, it should die down. If something suddenly happens, it should rise up again. Then you can start using engineering tools like EEG, evoke potentials, trying to figure out what is really happening. And tone-by-tone presentation, which is very hard to do. That's where you need electrical engineers for. You can look at fMRI to figure out what parts of the brain are really active or not active. And then you try to combine everything together in a coherent theory that you subsequently try to falsify, right? By the time you falsified it, you retire or you go on to the next topic, right?
You did have a rather interesting comment in our before lecture presentation here about specifically the need or the smartness of trying to identify which particular area of the brain is involved in this, that, or the other activity.
Yeah, Many people believe that specific parts of the brain are responsible for specific actions. I can't believe that. The brain is highly interconnected, although with a caveat there. The classic story is, right, there are 10 to the 11 neurons, 10 to the 14 interconnections. So it must be highly interconnected. But if you do the math, you'll find that one neuron makes 1,000 connections. There are 10 to the 11 neurons, so a small fraction, essentially zero chance that there is one neuron connected to the other neuron, right? So connections are most likely local, but local is relative. This is local, that is local, so there will be a chain reaction, right? So everything will be connected eventually. And I think you kind of see that. If you start doing fMRI analysis, you find that certain areas light up compared to other areas. But in the kind of research that we do, there are 4 or 5 papers that do the same thing, and they all find different answers. Now, who's right? Right? As an engineer, I look at this whole process and think, hey, what you're really doing is you look at brain activity under one condition, you look at brain activity under another condition, and you essentially compare those two activities. Both of those observations are very noisy. You subtract 2 noisy images. Engineering says you double the noise. So now you start interpreting very noisy pictures. Yeah, of course, you will find a different answer than I will find. And now we have to resolve that issue.
To what extent is there a correlation between the model that you're thinking in terms of and the mechanism that we're trying ultimately to explain, and that is the brain? Where are the similarities? Where would you say are the differences?
The differences are easiest to explain. The brain is made up of neurons, as we know, many connections, many synapses. There is no way we can build a model that has 10 to the 14 connections, 10 to the 11 neurons. I mean, that doesn't make sense. There is no computer in the world who can do it. And even then, if you could, then what could you do? We just have a brain in a box, and that's the same impossibility as the normal brain. So we need to make abstractions. Instead of modeling single neurons, we model a couple billion of neurons. We model cortical columns, in a sense, and we connect those columns. The interactions are still the same. There is inhibition, excitation, there is feedback, etc. So in that sense, it's similar, but at a much more global scale. And I think the way to compare it is, perhaps you know about Newton. When he was sitting under this apple tree, the apple fell and the laws of motion came to his mind. Well, Newton never bothered about the color of the apple. He never bothered about how many molecules are there in the apple. He took the apple and represented it as a mass. And who cares what the shape of that mass is, right? Now, that's an abstraction, but that still leads you to the right results. Until Einstein came about and his colleagues and said, hey, there is quantum physics, and really when you look at a much smaller scale, you cannot do this anymore. Well, that's fine, but the laws of motion still work, at least for speeds much less than the speed of light, right?
Let me go to a specific question related to, could you easily trace back the processes that were involved in the phone company's development of what you and I can now do, which is talk to a computer. Essentially, we can ask for a number, and with some percentage of accuracy, it will give us back the information we need.
Well, anytime I call my bank, I still refuse to speak to the phone. Since I hate repeating myself 4 or 5 times,
yes,
and even yelling the word yes or no 5 times before the thing understands it. Yeah, we've made great strides there. Computers can understand a limited vocabulary. If they know what you're talking about, they're quite good. But try to make an airline reservation. And it's sometimes very hard to explain to what city you want to go and at what time of the day. And don't even mention the word train or something else, since then it's completely out of whack. Okay, so you need to start using words, or limit yourself to words that are normally used in the context of airline reservations or telephone searches or bank operations. And we're not even near to understanding normal speech. Right? That's all simple commands, yes or no answers, or specific dates or numbers.
So you basically have to structure the input in order to get any predictable output.
Right. So what these systems do is essentially you have long lists of words for several words, 5, 6, 7 different pronunciations. Then you receive a word and you're matching. Do we find a match? With a fast computer, you can do that very rapidly. But that's really what it is. Now, I don't think humans do that. We don't really match word by word. I don't think any of you has ever heard my voice, but I think most of you can kind of understand what I'm saying. Right? So there cannot be a true matching there. Now, if I start speaking Dutch, I'll probably lose all of you right here. But again, that's another story. But then you'll immediately recognize that it is a different language. And you don't try to figure out, hey, what is he saying now in English? And that's another capability that we have, and I don't think computers will have anytime soon.
To what extent is there a similarity between that issue, which is at least partly solved, that is verbal feedback of verbal information, and what the post offices are facing with trying to recognize my scrawl on a letter versus your writing?
Right, they'll have a hard time either way. But they do a pretty good job. Since if you've looked at your mail for the last few years, at the bottom of the envelope you see these little vertical lines there.
Yes.
That's a sorting code, and there are actually machines that read your address, and especially zip code and house number, and try to generate these codes. And many times it goes okay. 10-15% of the cases some individual has to look at it, but that works pretty good. But again, it's in a very limited area, and the system is easily fooled. If you put the return address not in the upper left-hand corner, but in the lower right-hand corner, or left-hand corner, the zip code that you write there will be used to direct the mail, so you'll get the mail back. Okay, it's an easy test. If you want to waste 44 cents, that's the way of doing it. Okay, so the system has no notion of context, in a sense. It knows that there is an address somewhere in the middle of the envelope. It finds the postage stamp easily, since there is a phosphorus or a luminescent bar on it, and then it goes this way, and hey, there is a blob there, it must be the address, let's look for some numbers. Right, and it can get most of the time, the actual numbers.
Probably aided by the tendency I've noticed when there are computer-generated letters, what it tends also to do is put the zip code on the next line below the address itself.
Right, that helps. And of course, many times we need to help the computer. I mean, if you look at your checks, the account number at the bottom of your check is written in a very specific font, and that was specifically designed to make it easy to recognize account numbers.
The routing number and the account number.
Right, but then the dollar amount that you write in still has to be manually transcribed onto that check. So there you go.
Yeah, 50% of the errors in reading what I've written in, I would not be interested in. If they want to add value, it wouldn't bother me.
If you want to bounce it, well, if you want to hang on to your money a little longer, make a large signature that goes through the routing number, only with one line. Then it adds 2 or 3 days to clearing the checks, and now somebody has to actually read the routing number.
What was your intent?
Okay, so this is a free advice if you want to hang on to your money for a little longer.
What would you say is the key problem to be solved, if there is one, in trying to mimic by computer what our head is doing, what our brain is doing?
Well, I think we have to look at specific problems. I mean, our brain is doing too many things at the same time. So most of our brain is really involved in, well, I think there are only two tasks. One is recognition, being aware of the environment, processing the inputs, hearing voices, seeing the visual, auditory, everything. You're trying to recognize what's going on. And the other part is motor control. You need to move around. You need to sit up. You need to inhale. That's all under control of your brain. And I think that's probably the only two major parts. Both of these would be of great interest if we can solve them and build machines that can do it. I mean, we're talking about automated text processing systems, speech recognition systems. We're also talking about aiding amputees, brain stroke, brain trauma, whatever kind of patients. We're making great progress in both of those areas, but we aren't near where we are. Part of it is the scale of things. It still requires vast amounts of computer power to do it. In the mobility area, a major problem is making connections to the brain or to the musculature and keeping those connections for a long time without creating infections and have you.
Okay, I'm going to share with the audience one interesting comment that you made, and that is that I showed you the questions that we had reviewed when we did the interview 6-7 years ago now, and you looked down through a page worth of information that we were going to be talking about, and your comment I thought was interesting, and that is, gee, we haven't made much progress.
Yeah, right.
And in terms of fundamental questions, I guess that's correct.
Right, but there is progress, but at a lower level. 10, 15 years ago, people were thinking artificial intelligence is going to solve all the problems. Well, nobody has ever heard about AI anymore. It's kind of gone out of vogue. It simply doesn't solve it. Now, in the meantime, we've become aware that many brain disorders, especially psychiatric, are due to problems with the brain that can be solved by either chemicals or by stimulation, deep brain stimulation, or even building prostheses for the brain. There is great advances still in building artificial arms, artificial ears. There is an ear. There is an artificial eye that gives some sense of light and movement. Treatment of epilepsy is kind of working with stimulating the vagal nerve. So there is great advance, but we aren't there yet. And I think we have about another 500 years to go.
I was noticing that within the age group that most of our students come from, they have, as we have, enjoyed the arrival of telephone answering systems, and also, as you pointed out, the postal system and its increasing use of computers. But in any case, Professor Jansen, thank you very much for coming, sharing time with me.
Thank you for having me.
I will not test you on the remaining materials, so you don't have to stay if you don't wish.
Good.
But in any case, thank you.
Then I'll go back to my little cave. Okay.
University provided cave. Okay. So again, I apologize for the slowness of the invitation originally extended, but you could kind of plug that in intellectually at the end of the program on problem solving. That's where it would fit most effectively. And today what we're going to do is pick back up on the discussion of logical reasoning, which is what we had moved into from problem solving. And at that point, what I'm going to do is to pick up on just as a general reminder, where we were talking about last time in the logic of solving problems and reasoning about them, we pointed out that one of the things that is important to master is learning to falsify things. That is, in some cases, you can learn as much by falsifying something as you can by positively confirming it. And the two examples that I gave in that particular area were the thog problem, which is something that takes a lot of careful attention to solve, even when you're manipulating just the color of the object and its shape, and then generating a fit or a non-fit by something that has one but not both of two features that some independent authority has identified. And the parallel to that I gave you from real world experience was the fact that I was talking about an artificial problem where my parents had divorced, both of whom had remarried, and both of whom had had additional children by their respective partners. And that posed what turned out to be an exact parallel to the thog problem as we were talking about it last time. But the interesting thing is how you will remember that one of the fundamental things that our text author, Professor Matlin, talks about is the fact that you and I operate a lot better in the concrete realm than the abstract. And the data that I was going to point out, I don't remember whether I cited this last time or not, but when presented with the thogs problem, only 12% of a typical sample actually was able to solve that. And yet if it was couched in the form of half-sisters, the problem that we described in the previous lecture, 94% of them could get it correct. Same problem, just different ways in which it was couched. And that had a whopping effect on the difference of the ability to actually solve that particular problem. So today what we're going to do is to move into reasoning and recursion. Recursion is basically a kind of a mental sinkhole, if you want to think about it that way. John Morton published an article, my all-time favorite article. In fact, I like it so much I've memorized the entire thing. But what he did, unlike many of the other sources or any of the other sources that I've cited here in the lecture, what I'm going to do is to not only cite the article for you, I'm going to read the entire thing for you. And what Morton says is, in this article, further details of this paper can be found in Morton, brackets 1976, period. And so in essence what he's done there is he's referenced himself. And if you get into that too far, you find that you're wasting a lot of time trying to figure out what he's actually demonstrated. But what he's demonstrated there is a recursion, where something refers back to itself. And if you look then for additional details in the paper by Morton, 1976, what you find is assurance that there are additional details there. And the paper's referenced again and again and again. And you never quite get out of that loop. It's related directly to another form of difficulty, and that is what's called the liar's paradox. In that case, Epimenides, the Cretan, is credited with pronouncing, with great documentation, all Cretans are liars. And so basically, the given in that situation was Epimenides, the Cretan's idea that all Cretans are liars. And so the problem that you're stuck with is, well, is Epimenides lying? And if he is, then his statement is true. And yet if he's telling the truth, that is, if he's lying, then he's telling the truth. And so what you get into is exactly that kind of mental loop that will just keep you going forever if you can't break out of it. But in essence, the only way those kind of problems can be solved, both of them, the example that I gave you earlier from Morton and the liar's paradox, is that you really have to engage in what's called metacognition. That is, you have to think about the problem itself. To show you why it's necessary, let me just consider these two delights. In this situation, these rules control what actions you can perform with the given letters A and B. And what we're given is a rule set like the following. B can be replaced by BC. Any letters to the right of A may be doubled. BBB can be replaced by C, and CC can simply be dropped. You can drop it entirely. And the challenge then is, the problem that I'm posing to you is, can you derive AC from AB? Given the rules that I've laid out for you there, is it possible to work from AB to AC? And the answer, as it turns out, is no, you can't. you can't ultimately reach that as a decision. The difficulty is that well, there are two of them, basically. In essence, the one is that you can start with 1B, okay? That's all we give you. And secondly, what you're going to find is that no rule will actually ever generate multiples of 3Bs. So there's no way ultimately to get from AB to AC or anything else that would allow you to drop some, convert it into others, and so forth and so on. On my weekend activity as a carpenter, I stumbled across another favorite, what turns out to be a favorite example of mine, and that is the two boards problem by Page and Simon back in 1966. And that is that what they told us is the following. A board was sawed in two pieces, okay? One piece was 2/3 as long as the whole board and was exceeded in length by the second piece by 4 feet. How long was the board before it was cut? I'll let you play with that for just a minute and then come to realize that to solve either of these last two problems that we've talked about, you have to analyze the problem itself. And then what you do is come to the realization that this last one cannot be solved as it was presented to you for a couple of reasons buried in the facts that were presented to you. And that has to do with the fact that if you think about it, and I've got a crude rule measure there where each mark represents a foot for your comparison. And in fact, that was the board that we started with, was the 24-footer. And what we did then was to say that one board was 2/3 the length of the other board. So it's been cut there, okay? The one board that we cut was 2/3 the length of the other board. And yet what we're also told is that the second board was 4 feet longer than the one that was cut. And so the net result is that if you pile them all together, the only thing you can end up with is a board that is up into almost 40 feet. It's way beyond what you started with. So 2/3 that is 1/3 longer plus 4 feet than the original one that was cut makes it insolvable. The only correct mathematical answer is -12. -12 doesn't work when you're trying to build a cabinet. Trust me. I've cut some pieces that are almost that short, and it just doesn't work. So the problem cannot be solved because one of the two boards is simply too long relative to the total that you started with in that situation. Hence the recursion, hence the having to rethink and come to realize that the flaw lies not in the solution but in the problem. It simply can't be solved given the way it's been stated to you. Which leads us then into looking at I didn't realize I had an elegant explanation all laid out for you there. But in any case, what we're going to do is to just remind you that metacognition, thinking about the problems, becomes important. But more generally, what that's going to lead us into is some additional consideration on deductive reasoning and the final view of an intellect by the name of Leda Cosmides. She argues in favor of an evolutionary point of view of cognition, or cognition, I should say, and reasoning. In essence, what cognitive skills, what she's essentially asking is, what might cognitive skills add to our ability to adapt to a changing environment? Professor Jansen was talking about a couple of the major things that we tend to credit the brain with, and in fact that those are its major responsibilities in serving us. And especially as we find that let me come back to the fundamental question there, is what cognitive skills can you and I develop that would give us an advantage evolutionarily in terms of an environment that is increasingly populated by other evolutionarily skilled, cognitively skilled individuals? What would give us a selective advantage in that particular kind of case? Humans from the earliest times were both hunters and gatherers. So if you look from agriculture through the Industrial Revolution, what you find is that most recently we have benefited, of course, from the Industrial Revolution itself. And so these are cave paintings that were found. You will remember that Noam Chomsky stirred psycholinguist intellectual fires when he argued in favor of an inherited mechanism that permits extraordinarily rapid mastery of language. He was arguing essentially that we inherit our language. And there is considerable evidence that we've talked about at various times here to argue in favor of that. The very idea that among other things, in terms of classical presentation, in terms of presentation of classical conditioning, it is the case that we know that there are many repetitions before the conditioned stimulus is actively generated in response to the conditions that originally were leading to the UCS and UCR. That is, the conditioned stimulus and conditioned response take a long time to develop. And beyond that, if you think about language as being based on classical conditioning, we're stuck with the fundamental problem that when I'm doing as I am doing now, and that is using words in the absence of that to which they refer, by traditional classical definitions, classical conditioning definitions, I'm engaged in extinction. And certainly as you and I use language, we do not lose the ability to do so. That just doesn't happen. And so because of that, it would be the case that Chomsky might have very well argued in favor of that, among many other reasons, in favor of the idea that, in fact, we may have evolutionary mechanisms within us that automate, essentially, the acquisition of language. It happens much more easily than general learning theory would argue it should. And so basically, when I show you here, what you're seeing is a cave drawing, and that was a stampeding herd of deer. It's driven, if you'll notice, by beaters, okay? There's at least one here that's a little vaguer. There's definitely one here. There is part of one here, and there may be yet another one here. He may be running away from the charging herd. But in any case, there are several people who are equipped quite differently from the ones over here on the other side, who are the hunters themselves with bow and arrow. So that fundamental concept of cooperative hunting goes all the way back to Stone Age rock paintings in Cueva de los Caballos in Spain, which is where that picture actually comes from. And yet, if you look now at the Industrial Revolution, this is when once the last rail was laid in Promontory, Utah in 1869, locomotives from the Central Pacific flooded west and the Union Pacific headed east after they'd touched cow catchers there. And the link-up basically resulted in a significant amount of communication, among many other things. The Union Pacific, for instance, flooded the country with copies of the poster based on this particular picture, simply indicating now that it's possible to get all the way from the east to the west by rail. What Cosmides argues here is that we are both we are blessed with a schema acquisition device, essentially, that allows us to abstract and organize the pertinent information from our experience into helpful kinds of units and advice and so forth and so on, responses that we understand. And so the evolutionary pressure has basically refined those significantly. And it's those devices that basically maximize our ability to utilize language and master the environment of which we find ourselves, the changing environment. One of the things that's very helpful to humans and gatherers, she asserts, has been concerned with social exchange. We utilize the language in contracts, in face-to-face negotiations. I just haggled my way into a car here several months ago, and there was a lot of interaction between them, including a couple of times when I actually walked out. You save more money in the steps taken away from a potential car deal than you do standing there arguing with them, because the price magically comes down if you decide maybe you don't need that car after all. So in any case, essentially, Sternberg notes that evolutionary development of human cognition should facilitate the acquisition of schemas related to social exchange. And if you look at that, according to Cosmides, you and I are especially good in exchanges of information and goods and services and so forth. We're very good, you and I, at conducting what is called a cost-benefit analysis. And that is fundamentally what it's leading to, however you're doing it, what it's going to cost you and so forth, is do we benefit? Do I benefit from this particular exchange that I'm in the process of negotiating at this particular time? And so in essence, what Cosmides did was to compare subjects on deductive reasoning, predicting what their performance would be in terms of social exchange theory, the permissions-related schema, which is part of what goes into our various negotiations, and the abstract principles of deductive reasoning. And what she found was that among those three, socially based social exchange theory is the best single predictor of what we'll do in a discussion when we're negotiating with people using language and language skills. We define the terms. If somebody throws out a financial term about, well, it'll be flat billed until time X and you won't be charged any interest until time Y, and we'll give it to you interest-free for 3 years. But if you're 1 day late on the payment, you'll get 100% interest charge on the money we've loaned you. Those are the kind of things that you want to work out beforehand, and we use the language to do that. But the prediction of what we'll do in any given exchange of this money I have for that service or product that you have, and I may or may not want, all comes back to social exchange theory. The elements of that are the best single predictor of what we'll do by way of decision making in this kind of deductive reasoning process ultimately. So that she found basically that social learning theory predicted much better in 9 different situations that she set up where the negotiator has particular kinds of products that may be needed by another company, or skills, money, for instance. And then the other person has a product to turn over. And she generated 9 different examples of that, typical of what you and I run into in everyday life. And discovered, again, as I said, that social exchange theory was a very good predictor of the decisions that we end up making. So that kind of wraps up in a very fundamental and documentable way our discussion of deductive reasoning. It all comes down to whether you can answer correctly, am I being cheated? And document to your own satisfaction that you're not, that what you're getting is of value relative to what you're giving up, and so forth. That's basic fundamental social exchange theory. And in turn, what that gives way to is the other kind of learning, or reasoning, I should say, that we're going to spend some time with here today, even though this is somewhat different from the deductive reasoning that we spent so much time on previous lecture and so far in this one. And that is that basically syllogistic logic is also referred to sometimes as Aristotelian logic, because it actually goes back that far. It was Aristotle who originally developed the fundamental principles of syllogistic reasoning. It's older than the other forms of logic. It's older than deductive logic. And people who are performing it have been widely subjected to various forms of psychological research, because it's rich with the kind of things that you and I are constantly doing cognitively in terms of problem solving and so forth. And the various principles that I'm going to lay out here that are involved in documenting what syllogistic reasoning involves simply describe quite accurately what you and I normally do, even though there may be a cold, hard deductive logic that we could use that would generate the entire answer for us. One of the fundamental things on which syllogistic reasoning is based is the idea of a syllogism. And the syllogism itself is basically going to be deductive arguments that involve conclusions drawn from 2 premises. You can check in any of a number of sources to read in additional details about this, or even Matlin's book. I don't mean that dismissively. Matlin's book also talks about this in a very formal way. And that is that in the syllogism, what you've got there are basically 2 premises. So deductive arguments involving conclusions drawn from 2 premises are what's involved here. We've got 2 premises which are assumed to be true. That is, they're for the sake of working through the logic behind syllogistic reasoning. The assumption is simply that those premises, whatever they are true. And a conclusion then that is drawn from those 2 premises. So this is the other way. This is the way our text defines it, actually, and it's essentially the same thing. It's interesting that if you go back through earlier definitions of Matlin, at one point in the definition she used back in the 2001 text, at that time she did not even require in the definition that she used that the conclusion be drawn from the 2 premises. So you might have been talking about apples and oranges and reaching conclusions about bananas, given the looseness of the definition that she originally offered. So it has been tightened up over successive generations of that particular text. And it quite closely approximates what many others would now confirm. And that is simply a deductive argument that draws conclusions from 2 premises. Those are the key elements, the premises and the conclusion. So when we start talking about the syllogism, we can then define the premise as I'm talking about it. And that is essentially a statement, a proposition about which an argument is made, a statement or a proposition about which an argument is made. The goal here in syllogistic reasoning is to produce reasoning which is not inconsistent with the underlying logical forms that are used when the premises are all fully spelled out. That is, one easier way to do this is simply, anytime you're doing a contract or anything like that, it's of course much easier to just do a general description of party A will do this and that and so forth. But it turns out that in order to protect yourself, you end up having to spell out in detail exactly party A will do this, but by this what we mean is paragraph 1, paragraph 2, paragraph 3, and so forth. And so the goal is basically with syllogistic reasoning to reach a kind of a shorter form way of getting to the end that you're ultimately after here. Each premise constituting a syllogism, that is, that makes up a syllogism, specifies a relationship that exists between two categories. A and B, for instance, are the ones that we will focus on. Each premise constituting a syllogism specifies a relationship that exists between those two categories. And so a syllogistic reasoning is sometimes also called categorical reasoning, which can yield different kinds of forms. There are several different ways in which categorical arguments can be developed. And that's going to introduce us to what are called Euler circles. Okay? These are not named after the Houston Oilers, present or past, but rather simply are pronounced in the same way. So you can think of Euler as in the former football team to pronounce E-U-L-E-R correctly in this situation. It's not named after them, but it's pronounced in the same way. And what's basically involved here are various premises which can be created and diagrammed in terms of using circles, called Euler's circles. One of the forms of those is essentially circles that represent what are called the universal affirmative, which is the simplest, and we're going to reach some degree of complexity before we go through all this. But essentially, a universal affirmative would be a statement or a premise such as all A are B. That's an example. Real-world example would be all Cougars are loyal alumni. That would be one form of all A are B. A being the Cougars, B being loyal alumni in that situation. Another one, all isosceles triangles have two equal sides. All isosceles triangles A have two equal sides B in that situation. Using the circles, we can depict this all A are B in the following manner. Okay? This is but one diagram of that particular premise. Okay? And as you can see here, in this particular case, if A is represented by the A circle here, given that it's located within as a subset of all of the things that might be captured in the B circle, what this implies here is that there are some B's that are not A's. That is, there may be loyal alumni who are not Cougars, which is quite reasonable if you happen to have graduated, say, from Notre Dame or the University of Southern California. So in that case, such people, such other college graduates would be in the B category. They may be loyal alumni, which is represented by B, but they don't happen to be Cougars. And so our original statement, all A, all Cougars, are loyal alumni, would still fit in this situation, even though there are exceptions, as represented in the broader B category here, that may nonetheless include loyal alumni who don't happen to be Cougars. There's another possibility. What if all people who are alumni are Cougars? Then we have a correct definition of this if we do it this way. That was the one we utilized and described, but this, as it turns out, logically also explains or diagrams all A are B. And what that's going to lead into is a discussion around how we define sum, and there are a lot of debates swirling around that particular issue, but it has to do with the definition of sum in that, or all. What is implied by all, what is implied by sum, as we'll get into it a little bit later here. So as I'm saying, what if all people who are alumni are Cougars? Then we've got the situation on the right. But if they happen to graduate from other people, other places, and be loyal alumni, then we have to diagram it this way, not this way. Which leads us into, then, a couple of other observations. That is, in the argument, in the statement, all A are B, it can be understood in different ways. One of them has to do with the fact that each is equally important to understanding the logic based on the premise. And for this premise, it may or may not be reversible, which is one of the vaguenesses that we'll get into here in a little bit. But in essence, in some situations, all A are B, and that would be true here if we reverse it. All B are A when this describes, that is when the only kind of alumni we talk about are cougars. Then if that were, if everybody in the world with a college degree graduated from the U of H, then we could diagram it this way. All A are represented by this circle, but so are all B. All cougars are loyal alumni. But this obviously does not describe the situation where there are other colleges also producing alumni. So we have to diagram it in a couple of different ways. That statement, all A or B, may or may not be reversible, as I'll show you a little bit later. Let's look then at a second form. If we have a universal affirmative, we might as well also have a universal negative, and sure enough we do. In that case, logically, debate-wise speaking, we're going to be looking at a statement like no A or B. So we could make an illustration of that would be something like no cougars are Aggies. Or actually, to be more current, we would probably use something like no cougars are Memphis Belles, since they're both in the same conference. No right angles are less than 90 degrees. Again, no A or B. It can be represented only as depicted here. In that situation, anything that is an A cannot be a B. So if you're a Cougar grad, you can't be a Memphis Belle. You can't be a grad of the University of Memphis as your first bachelor's degree. Obviously, you could transfer schools and graduate there instead of here. But for all practical purposes, if alumni is going to be defined as graduates of the University of Houston as your first undergraduate degree, no University of Houston graduate at the bachelor's level can be a graduate at the bachelor's level of another institution and still claim original alumni status, okay? All right, I'm dealing with a somewhat vague definition here, but I'm tightening it up for you so you don't worry about it, okay? So in this particular case, there's only one way in which this can be interpreted, and that is also of interest, and that is that the reverse also happens to be true. No B's are A. So no A or B is universally reversible. Because if it's true that no A is a B, then no B can be an A. And so this one is absolutely, it can be stated either way with equal confidence and truth value. So yeah, no A or B, but equally true, no B or A. So we could reverse these two letters and still have the same statement and still have the same diagram. It is logically what is called reversible. And then we get into two other possibilities, and here's where the wrinkles begin to arise. Not no B or A, but rather when we start looking at not the universals, but rather particular affirmatives. Here we're beginning to get into some rather interesting arguments or premises that would be possible in this situation. For instance, one of the statements that would fit and classically illustrates what's called a particular affirmative is the assertion, the premise, some A are B. Some cougars are women, okay? This one is much more complex because there's not one, but there are actually four possible ways in which to interpret this statement. Let me show you what they involve. One, coming back to our use of the word some earlier when it means all, some, well, the particular sum quantity happens to be all, means this statement could be used to diagram one situation where some A are B. But there's another way to do it, and that is instead here. This is again pushing the sum category to its maximum limit in this particular case. In situation B, some A are B. Well, as it turns out, all A are B, but argumentatively, legalistically, you could say here some A are B. It implies that some A are not B, but that is not stated when all we say is some A are B. It's making no statement about other characters in that particular situation. So again, some cougars are not women is a legal statement. We could also do it this way. Again, the operating rule there is some A are not B. And that's, in this case, coming closer to what you and I most often tend to think of and intend, and that is when you have a bigger A category,
you have a B group which is buried within it. Some A are B is what we would have here. That is, the characters in the larger circle include those who happen to also have feature B. Okay? And so again, some cougars are women, fits here. If A represents all cougars and B represents the female component, obviously the males would represent the other component there. There's another one. And that is, this would be a fourth way in which we could diagram it. This one is a cleaner way to look at it. But it's not markedly different from the third way, and that is some A are B, meaning that it's only the group that's in the overlap category here. That is where you're classified as both a cougar and as a woman. And so if A-ness is cougarness and B-ness is womanness, then in fact some A are B would represent cougars. Would represent females that are cougars in that kind of a situation. So again, in this particular situation, the statement can be reversed. Some women are not cougars. But there are also situations included in the diagrams there where the statements can be interpreted so as not to be reversible. Think about the following. Some animals are not sheep is true, but that does not mean that some sheep are not animals. Okay, that simply doesn't reverse in any meaningful and logical way. The logic can become quite complex with this kind of logic in particular, more generally the classes that I'm talking about. But if you make an overall statement like some Iraqis are not field hockey players, as a statement it leaves us with the following, and that is that there may be some Iraqis are field hockey players, but we'll never know. Okay? It's not logically necessary that some Iraqis play field hockey just because some of them don't. Okay? And that's, again, captured in the circles. This last set of statements opens the door for the primary reasons why we actually pay attention to the particular situation here. Let me back up a little bit. I want to go back and make sure I only told you correct things about. That's why people were looking at me funny. See, you guys need to stick your hand up when I get astray here. And that is the last couple of statements that I'm talking about. Really, we're dealing specifically with particular negative. You may sense, and it's generically true, I can show you test results. I've always had difficulty with Euler circles, so watch me when I'm laying this baloney on you. In some cases, I speak less than truths. The only time as a professor that happens. But let's go back and look then at some A are not B. Some cougars are not women. And there are three possibilities in this particular situation, as indicated here. Some A are not B in this diagram. Some A are not B in this diagram, as we showed you earlier. And in this case, some A are not B in this situation. So in all three, those are all ways in which you could diagram the sentences. Some cougars are not women. So if we make these be the cougars and these be the women, then in this case, the A, the cougar category, is larger than those cougars who are women. And as is true, and in true here, if some cougars are not women is also illustrated here, because all of the group where my pointer now is are not are not characterized as B, i.e. women, in this particular situation. So in this situation, again, the statement can be reversed. Some women are not cougars. That's where I caught myself earlier. But there are also situations where the statements can be interpreted so as not to be reversible at all. And that is the some animals are not sheep, which is true. Some animals are not sheep. But in fact, we can't reverse it and say that some sheep are not animals, because all of the sheep that become animals, the only situation that will work is this, in describing that when it is irreversible. In this kind of a case, you would not be able to reverse the logic here. So the other example that I was leading into here is the idea that some Iraqis are not field hockey players. Okay, but there may be some hockeys that are field hockey players, and we'll never know whether that's true or not. But it's not logically necessary that some Iraqis play field hockey simply because some do not. That's simply the one does not imply that the other has to be true. So it's these last sets of statements, as he finally gets himself straightened out here, that open the door for the main reasons why psychologists end up looking at syllogistic reasoning. And there are really two fundamental reasons that are of importance here. One is the idea that reasoning logically requires that you reach only those conclusions that are possible given any of the logical interpretations that can be given or properly attached to the premises. That is, with the premises that are stated, what are the logical conclusions that can be drawn out of it? And how we go about doing that, how we go about problem solving, matching a given situation to another, and figuring out whether there is similarity or not, is fundamental to what cognitive psychologists are really looking at. So we're only interested in the defensible solutions given the limits of the problem that we've specified. And then secondly, because we do not always logically work out all those interpretations, our reasoning is based on processes that are governed by how the premises are encoded. That is, what we tend to do is convey a lot when we set up the premises relative to the conclusion. That's where contracts tend to break down. If you don't lay out in specific detail what you're paying a contractor to do, he or she may simply not perform that work, and you can say, yeah, but what I meant was, well, the contract is all that you're legally required to meet, and that's all the contractor is specifically, not previously, specifically required to meet is in that situation. And so basically it's that, even that second one, that we do not always work out all of those interpretations in our head. But our reasoning is based on processes that are governed by how the premises are encoded, and we spend a lot of time in contracts working out the premises, the specific language of the context, because that is all that governs what you can extract from that by way of conclusions. So if a given product has not been required, or if the quality of the paint or the thickness of the garage door or any of that is not spelled out in the premises of your contract, the if part, you're hung when it gets to then if the other person has a different interpretation or was thinking of something different when that contract was originally written. We do, as you can see from the vagaries of what I'm talking about, also tend to commit some errors when we're engaged in syllogistic reasoning. And the nature of those errors is itself rather revealing. And so basically, the problem is that the correctness of the conclusion depends only on whether the conclusion follows logically from the premises, as I was saying with the specific example. The actual truth is irrelevant in this kind of a situation. We naturally tend to have difficulties separating our beliefs, as I was talking about the contract a minute ago, from the forms of argument that the contract actually takes. But you need to, when you're developing a contract, that's the reason you hire a lawyer, is to work out and anticipate all the things that could possibly go wrong with this particular kind of wording, because that's critical to all the Euler circles, the various forms that we've been talking about earlier here. We may accept things because we believe them to be true, or reject things because we believe them not to be true, regardless of the underlying truth. I mean, we're human. This is the intrusion of world or background information. I like that phrase. It's in an article by Galati back in 1989, where he was analyzing our reading. And when real world or background knowledge jumps in to alter how we reach a particular kind of conclusion, it does not invalidate the logic underlying the reasoning itself. Beliefs is one thing, documentable logic is something different. So where you may believe that you had in mind that you were going to have the painter do this kind of a job and another kind of a job results, that's the problem with beliefs versus what was actually put into the contract. Let me give you a specific example here, and that is what's called the Sander parallelogram. I'm sure you've tripped across this at some point or another, but this is a parallelogram with the following kind of features. Let me also argue, I fussed with this thing for hours trying to get it correct. It is generally suggestive of what I'm talking about here, but the words are to be believed, not necessarily features of the diagram, because, believe it or not, I'm going to be premised on the idea that this line is in fact equal to this line. It may not look quite that way, but it's part illusion that you're dealing with there. And so basically what the Sander parallelogram represents is an illusion, okay? Given that the angle, and let me trace these out for you, C AE. I misindicated there. The angle CAE. In other words, this angle is the same as this angle, ACE. Okay? This angle, angle C here, is the same as that angle. Okay? That's the premise. That's the given in this particular situation. Okay? We know from plane geometry that if two angles are equal, we have an isosceles triangle in this case. And thus the sides opposite the two equal angles must themselves also be equal. And so basically what I'm arguing here in terms of this is that if the CAE angle is the same as the ACE angle, what that is telling us is that angle A in the CAE combination is the same as angle C in the ACE combination. And that's where my diagram is fouled up a little bit, but essentially what's being argued is that this ends up being the same lengths as this, because this, the AEC, is an isosceles triangle, okay? And therein lies the illusion, okay? So from this, basically, we can reason that AE and CE are sides that are opposite equal angles. So if we're saying angle A, as defined by CAE, is the same as angle C, defined by ACE, it means then that where these two project are equal. So in following ACE, this angle is projecting toward this side, this line. And I'm arguing then that the CAE angle, that is this angle, is projecting toward this side. And what that means is that this overall figure, ACE, has to be an isosceles triangle, which means when you bury it in the context of a parallelogram, it certainly looks as though this line is actually longer than this one. But I've just demonstrated, given the laws of plane geometry, that in fact they are the same size. Okay? Therein lie illusions, and that is that you know, the processing that the language goes through, that the brain goes through in coming to our judgment that in fact AE looks a lot longer than EC may be appearance, but in fact it's not fact. That is, that we can demonstrate, given the logic of plane geometry, that in fact AE has to equal CE given the manner in which the figure was originally constructed there. And there comes back to the logic of what Professor Jansen and I were talking about earlier, and that is that it's one thing to know that the equipment doesn't function, doesn't reach the right conclusion. Illusions are an exercise in not reaching the right conclusion. But in fact what that is a performance limit, which can be determined ultimately by looking at how the brain itself actually functions. So you're fundamentally assuming, okay, so we made an error. It becomes interesting then to figure out, well, okay, why did we make that error? What is it about our processing that leads us to reach that wrong conclusion? So the disagreement with our senses, having just been demonstrated logically to be, logical and correct, or not logical, but empirically correct, is essentially one example of the use of a particular kind of problem, that is the Sander parallelogram, to illustrate some of the errors in reasoning that we can encounter when we're dealing with syllogistic reasoning. We also have atmosphere effects, and essentially in that we are right in the heart of what psychology is dealing with. Woodworth and Sells, way back in 1935, suggested some premises create an atmosphere which fosters certain types of reasoning errors. Okay? One example that is often cited is this one. Some A are B. Some B are C. Can we or can we not therefore conclude that some A are C? And that's an atmosphere effect. If you reach the wrong conclusion in that, what you're subject to is an atmosphere effect. Okay? Notice, for instance, that this one is simply not correct. Because if I give you a statement like, some men are Texans, some Texans are women, and therefore some men are women, some A or B, some B or C, and some A or B, some B or C, and therefore some A or C, does not work in that situation. Okay? So what's established there is a sum atmosphere, the idea that you're thinking generally in terms of some of the time, X, Y, or Z. And what that does is to encourage us to include or to accept a conclusion of some sort, pun intended. And that is to accept a conclusion of some sort. And in fact, it doesn't always work. There's another atmosphere that can also be established in terms of a negative atmosphere. That is, in addition to the sum effect, we can also talk about negative effects. So if we talk about no A are B, all B are C, therefore no A are C, and so what we see here is no A are B, all B are C, and therefore no A are C. Doesn't work. Again, we come back to the Euler's diagrams as a very effective way to illustrate and work out mathematically the logic and wisdom or the lack thereof in the various conclusions that we're trying to reach. So the diagram represents the correct solution of the problem, and that is that this is not good logic in this case. And again, it comes back to our definitions of the various terms here. Chapman and Chapman did an interesting study on, oh, sorry, I didn't realize I had another example for you. Here. No A are B, all B are C, no A are C. And you can again see a situation here where it's clearly the case that in fact, some A may be. And then we can look at the work of Woodworth and Sells. Sorry, I had jumped ahead to the Chapmans, who did a study on conversion errors. What they did was to talk about, what they studied was cases where you and I sometimes make illicit conversions of the various kinds of premises. We combine them in ways that are simply not justified by the wording of the premise itself. We talked about at least two legal conversions, okay? In the universal negative, no A are B, then no B are A. That is a conversion from one form of the statement to another that is perfectly justified by the diagram that we can create here. And the other one is essentially in the particular affirmative, I should say, some A are B, then some B are A. That's another reversible statement as indicated by the situation here. But if you consider the following, all A, hang on a second, I'll get to it. All A are C, all B are C, as we described earlier. Therefore, all A are B doesn't work. So that some of the conversions that you're kind of encouraged into making by particular all this, all that statements don't necessarily work. The diagrams come back to show us mathematically what we're talking about more precisely in that case. That is, they define for the eye what we're talking about in any of those given premises. So this same diagram that we just used also depicts this situation and shows an example of why it cannot always be true. Begg and Denny in 1969 showed that both the atmosphere hypothesis and the conversion hypothesis, the last two problems that we've talked about here, predict similarly as to what types of errors will be made in syllogistic reasoning. What turns out to be important here, as I've been kind of intimating in leading through this particular area of discussion, is particularly the interpretation of what we mean by the word some. Some people are human is true, okay? It implies some people are not human, but that is not what was stated. Think about it again. Some people are human. You and I might cite particular friends and immediately be willing to leap to the idea that some people are not human. But in fact, that's not logically justified if the only statement that you made is some people are human. Some really normally is interpreted to mean some but not all. That is the meaning that most of us tend to attach to the use of the word some. The problem is common usage versus usage in logic. Okay, therein lies the difficulty that we have in that situation. For instance, consider the following, and hang with me for a minute on this because it takes a second to diagram in and you'll see the problem that I had. Begg, in the late 80s, did a problem where he told subjects that a group of people consisted of 20 artists and 20 writers. So this is the overall group as represented in the diagram I'm going to create here. And those are the artists are simply the proportion of the group that is cut out or defined by the green curve, okay? You'll see the problem I have when I now define for you the writers, because in fact those are outlined by the purple line here, and it implies it's the same 20%, but what I'm depicting here is that this group is the purple group, if you want to think about it that way, okay? And that is that the artists are represented by this slice of the pie. The writers in this 80-20 split represent the rest of the pie. So it's diagrammed by a line at the same point, although you can see the problem that I'm having descriptively here. So in this case, the second fact that was given, other than the fact that 20% of the group is artists and 80% of them are writers, the second piece of the information is that half of each are men. And so if we look at the artists, what I'm also telling you, in addition to the 20% artists, 80% writers, is I'm also telling you that among the artists, half of them are men, and logically enough, that leads to half of them are women. What else would we have? I'm also telling you then that half of the writers are women and half of them are men. Given this diagram, what we can say is that some men are artists, okay? Some men are writers. Both of those are easily justified given the diagram that's been created here. Some women are artists, some women are writers. That can also be justified there. Statements identifying more limited classes were rated as more acceptable, interestingly enough. One of our usages is that some may mean less than half. If you go to Webster's and look up common uses of some, you find a rather interesting division. That is, what Webster's acknowledges in the dictionary of spoken English is essentially, the written English for that matter, is that what we mean by some is being an unspecified number or part of the entire object. In this example that we've given you here, artists were some of the total that were represented, as were writers, okay? But a second way that it can also be defined and is frequently used is being unknown or unspecified by name. That also implies some, as that can be used. And thirdly, in terms of logic, what is actually implied by some is being part and perhaps all of a class. Therein is the hang-up, okay? The third definition of some is that of being part and perhaps all of a class. We conclude that our normal use is useful for successful communication most of the time, but its use in logical argument may lead to an imprecision in the overall process of deriving from our premises whatever it is that we're trying to communicate in a given situation. Let me show you another form of mental model, okay? And that is essentially one that involves variations on the atmosphere effects that we've already talked about. Johnson Laird in 1983 and again in 1988 has studied the mental models we developed to represent syllogisms. Let me back up and describe or define the English there, because Johnson-Laird is a hyphenated name, single subject and therefore single verb. So it is correct to say Johnson Laird has studied the mental models and we developed to represent syllogisms. Okay? Decisions, he argues, are based on checking the conclusion against the models that have been created. And thus, in essence, what we do is to study the models to predict the conclusions that will be endorsed in any given situation. Okay? And his particular focal point is studying inferences about mental representations of the various syllogisms and premises that we create in a given situation. And so what he's going to do is to lay out 4 different premises here during the course of our discussion of his work. Okay? So let's give you an example here. First premise, all A are B. And I'm going to give you as the example what's on the screen here, and that is all of the let me try it again. All of the applicants are banana lovers. I've tried to come up with A, B, and C that were relevant here, so give me some language problems. Okay? Imagine the applicants and tag each of them as a banana lover. Okay? In this case, you may want to move the screen a little bit further to the left and up because we're going to be headed to the bottom right corner of the picture here. Okay? So the arrows in this diagram represent is A. So what is diagrammed there is applicant 3 times over. Applicant is a banana lover. That's what I'm starting with as the A is B, all A or B premise. Okay? And so we imagine the applicants and we can simply attach a tag to each of them. The second premise here is that some banana lovers are cute. That is, some B are C. So we can argue then that we can tag some of the banana lovers as cute. That is, by C. The conclusion that some of the applicants are cute would make us argue that some A are C. But in fact, you can see the problem here. And that is that what we can do in this particular situation is, sure, take all the banana lovers, but it turns out those don't happen to be the ones that are also cute if they're applicants. And the net result is we may lead to an incorrect decision. We'll pick it up next discussion.